Good afternoon, all of you. So we are very close to our lunch, so I'll try and make my presentation very, very short. When Reggie asked me to talk about dynamic line rating, I was actually wondering why is he asking me to do this? Because 27 years ago, my first job after I finished my engineering was actually calculation of line ratings and line impedances. So I was wondering what is new about the line rating. What is new is that there are many new concepts and initiatives, particularly integrating renewables, that has developed some needs as well as opportunities for working in this area. So what is DLR? Simply put, it is the overload rating of transmission lines. But life is not so simple. DLR is the real-time transmission capacity of transmission line considering the sag, weather and current conducted at any point in time. So there is a safe rating for the lines, but we can actually stretch it a little bit more by considering the real-time conditions of weather and other operating conditions. And that is what we actually call it as dynamic line rating. You can see in the orange space, that is the static rating as we call it. That's the normal rating of a transmission line, or I would say any distribution line as well. And the green area is the area where by using smart grid technologies, we can actually extend the rating of the line for short periods of time. So here is an example where you can see the static rating, which is an orange line almost in the middle of the picture, middle of the slide. And then the actual load is generally below the static rating. But for a brief period, the load exceeds. And then normally this would be considered as a violation of the dispatching regulations or loading regulations. But what we could be doing is with the dynamic rating, in this particular case, the dynamic rating is slightly higher than the static rating. So we actually optimize the line rating by using different calculations. Here is another example. The green lines are the dynamic line rating of the line on any time, which is actually computed, calculated. The red one is the static rating, and the blue one is what we call the ambient adjusted rating. So it's actually a slightly safer, a more aggressive rating of the line, and you can actually stretch the line to that level if there is a need. As it arises. So one more example of the same. So right at the top, the line is, it's the real-time rating of the line. Then you have the pink color, which is the load, and then below that, based on the conductor temperature, and so on. So why do we need DLR? As the vision of my last company where I worked, it was do more with less. So we have already built some certain transmission lines, certain capacities. Why not try to extract the maximum out of the installations that we have already made? Maximizing the performance for shorter periods of time in order to make power systems. Just show one or two slides later on how we could probably do this. And to the other aspect is to take cognizance of the impact of weather. I mean, wind is one of the key things that determines the rating of a transmission line. And we all know that during the windy conditions, the wind farms have been generating more power, and that's the time you actually need to transmit more power. And why not make use of this fact and increase the line rating whenever the wind is more, when wind speed is high. So in fact, the DLR, one of the key requirements or applications is actually for evacuation of wind farms' intermittent energy. So the benefits of DLR, it's cost effective because we are just putting some extra technology, sensors and equipment. It is congestion relief, so it gives you good relief for short time congestions. It cannot address long-term congestions. Improved grid reliability, so as we saw in the earlier sketch, so if we could only allow on very short terms the line rating to be increased, and today there are even relays with the DLR settings. In Schneider Electric, we had one relay which had this DLR setting. So you could use that kind of applications to actually ensure that the system reliability actually increases, and we are not going to switch off the grid because of transient load increases. Optimized asset utilization, instead of building a lot of transmission capacities just to cater to the peak, we can actually use DLR. I would say DLR is the reverse of DR, because in DR we are basically looking at curtailing the load, but here in DLR we are actually enhancing the capacity to deliver. Okay. It leads, obviously, when we have better utilization of assets, it leads to lower costs, hopefully, true line capacity in real time, improved transmission efficiency, faster integration of wind energy. As I mentioned, we will just see a couple of slides. So this just goes back. I mean, I picked up this picture. It's a 1970 IEEE picture, so nothing has changed. So this is the picture that I probably used when I was in my schools learning about heat in is equal to heat out. Okay, that's the basic of DLR. So you have the solar radiation and the I squared R losses in the conductor, and you have certain dissipations along the conductor, and we have to equate the two. Generally what we do is, when we do transmission line design, we take the most conservative factors, and we don't take into account the real-time factors. And DLR is all about taking the real-time factors and then allowing the line to transmit more whenever there is a need. So the factors affecting line rating are current carried by the conductor, conductor size and resistance, conductor clearance to ground, cloud shadowing, maybe a few percentage, and total eclipse would result in approximately 18-20% capacity increase. Wind increase of 1 meter per second at 45 degrees would be 35% increase in capacity, and if it is 90 degrees, it would be 44% capacity increase. So this is just, it's really unharnessed power of dynamic line rating. So we can really achieve a lot. I'll just skip these in want of time just to show you. Basically what this shows is how the tension on the line or the conductor behaves when there is wind or there is no wind. So here is an example which is a tension-based DLR. Tension-based dynamic line rating systems for overhead transmission lines. Basically you have to install some load cells that will determine the tension on the transmission line, and then you need to find out what is the radiation, the solar as well as the conductor radiation, and then you need to integrate this and evaluate what is the real DLR. So it's just another picture of the load cell being installed on the transmission line itself. So just to compare the different cost-benefit, ratios. On the left, you find the different methods, I would say. So purely based on weather only, or conductor replica, or temperature, tension, sag, and combined. So you find that the first two, weather and conductor replica, these are purely calculations. There's no real sensors to be installed, etc. Whereas temperature and tension and sag, where you need to put some sensors in place and you really monitor real-time situation, and that will give you a relatively good load increase. So I'll try and skip this. Mainly, I think the key ones are the tension-based method and the sag-based method, and they actually take into account almost all the other factors that we talked about with reference to temperature, wind, etc. So I just picked this up because it was just coming to my mind. We've been talking about the problems in Tamil Nadu, and I think in the Powerline magazine that you have in your hand, there is one article about the power crisis in Tamil Nadu. And we also know that, one of the problem is that there's about 7,000 plus megawatts of installed capacity of renewables. 7,000 of wind in Tamil Nadu. And the article also says that when they wanted to buy the power which Delhi returned to the center, they could not really buy the power because of lack of transmission capacity. So the power had to be given to other states who had the capacity to draw. So in Tamil Nadu, the main issue has been the evacuation of wind power, and the colored districts are the ones where the wind farms are maximum. So they are in the southern part of Tamil Nadu, and in that part, the load is not very high. So literally you have to evacuate everything. And now Kodangulam is right at the tip, at the bottom. And the southern part of this picture is also the area where solar radiance is very high. And Tamil Nadu they have announced the solar policy. And there's going to be a lot of solar generation in the southern half of the state. And that energy also has to be evacuated. So what they are doing now is, on a very urgent basis, on a war footing, they are building a 400 kV transmission line at a huge cost of something like 4,000 crores, and the work is going on right now. So, and then the second phase of that will be to build a 765 kV transmission system. So my question was, I don't think we can do away with this. I mean, we will need investments in the transmission systems. But could DLR have helped us in the short term while the transmission networks are being installed? And I believe very strongly that yes, I think we could have used DLR technology to take care of the intermittency in wind generation. Okay, to summarize, basically static line ratings are based in worst case estimates of weather conditions and are usually system wide, whereas dynamic is based on real time basis. And if implemented correctly, dynamic ratings should not reduce reliability but actually increase the capacity. So thank you very much.